Whenever light passes through a finite aperture, for example when passing through lenses or a slit, diffraction occurs. This diffraction results in the fact that the light waves also propagate into areas that cannot be reached in a direct line. Diffraction is not only limited to light waves, but also occurs with sound waves and is the reason why we can hear sound even without being in line of sight with the source. Which areas behind an object are illuminated by diffraction also depends on the wavelength of the light. This can be observed, for example, in the rainbow pattern on one side of a CD. In areas in which illumination occurs, one speaks of constructive interference. Components from different spatial areas accumulate here. In the dark areas, destructive interference occurs. The components from different areas cancel each other out. In this experiment, diffraction at a grating is used to determine the wavelengths of different spectral lines in mercury. The measurements are performed on a grating spectrometer. The diffraction grating is placed on a turntable. It is illuminated through a tube with the light of a mercury vapor lamp, which contains the different wavelengths in the visible spectral range. The diffraction pattern for the different wavelengths occurring behind the grating can be observed through a telescope. This telescope can be moved around the grating to observe the angles at which the diffraction maxima of the different wavelengths occur. An angular scale on the swivel arm allows the measurement of the diffraction angle relative to the incident beam with the accuracy of an arc-minute. On the coarse inner angular scale, the angle is read off in degrees. The value on the finer scale, which best matches a mark on the coarse scale, is added as an angular minute. First, the spectrometer is adjusted without degrading in the beam path. The mercury vapor lamp is placed behind the tube and switched on. Then the telescope is aligned and adjusted so that the narrow slit in the tube is in focus. With the lamp switched on, note down the angle of the telescope as a reference value for the initial position. Repeat this procedure to determine the reference values 3 times. Now the diffraction grating is placed on the turntable in such a way that the light beam enters the grating as perpendicularly as possible. Be careful not to touch the sensitive grating directly. By turning the telescope, diffraction angles are determined under which the first and second diffraction order of the differently colored spectral lines appear. The distance between 2 grating lines can be determined from the grating constant specified on the diffraction grating. The recorded values for the diffraction angles are corrected by the reference value for the incident beam. For the different diffraction maxima, the wavelengths of the spectral lines can now be calculated from the grating equation. The resulting values can be compared with literature values for the spectral lines in mercury.